the co-perpetrators, organizers of this workshop. Thank you for all your efforts to bring this together. So Natalia is a professor of economics at Carlos Tercero in Madrid, where she also had something called the Energy Eco Lab, which is a newish organization.
Yeah, it's a new lab, so we just want to bring people working in energy economics together so that we can push it forward.
I hope you organize a workshop and invite us all sometime.
Of course. When it's sunny weather in Madrid, yeah.
Yeah, we always have sunny weather here in Cambridge too, or occasionally. So Natalia is also a research fellow at the Center for Economic Policy Research in London. She was a recipient of the Salvador Herrero Prize for Best Young Spanish Economist, and very honored to hear what she has to say. Her nemesis is Hannes Veit from the University of Basel, who is in the back, and he'll be asking his question, and we'll also have 5 minutes for more general discussion at the end. So Natalia.
Thank you so much, Ben. Thank you so much to INI for hosting us here, and Andy for doing such a great job in organizing this. So today we have a great panel of economists who are going to be talking about many of the issues that indeed David talked about, so that you can see that we economists working in energy economics have a very rich and coherent research agenda. Bert is going to be talking about flexibility, Par is going to be talking about capacity, Richard is going to be talking about storage, all those issues that David pointed out as being key in designing the best way to achieve this low carbon future. And my aim is to contribute to these debates by talking about competition among renewables. This is joint work with Gerard Llobet at CEMFi, another research institution in Madrid. In this audience, I think I don't have to go through the fact that there's certainly among European countries ambitious renewable targets. Renewable targets are set in the horizon 2020, 2030, and in order to reach those targets, certainly the power sector is going to be playing a main role. One of the most effective ways of increasing renewables in total energy consumption is to deploy more renewable generation. So the question is, one of the questions is, are we going to achieve those targets? Is it just a matter of setting the objectives, or we have to do something in order to induce investors to really invest in these technologies? And one of the first issues that came to our mind when we started working in this project is, under the current market arrangements, if we invest in new renewable technology, and we know that by 2030 over 2/3 of total electricity generation are going to come from renewables, do we know how these markets are going to perform when we have all these intermittent zero marginal cost resources competing in the market? How are these markets going to perform? Certainly, we have to deal with a two-stage game. Let's say in the first stage, we deal with investment decisions. In order to know whether investors want to invest, we have to be able to solve the second stage of the game. And as far as we are aware of, the second stage of the game, that is competition among renewables in a renewables-dominated system, has not yet been characterized. We believe that the shift from fossil fuels to renewable generation really brings in a new paradigm in electricity markets for several reasons. In these papers, we're going to be focusing on everything that's got to do with competition. And when we talk about competition, we want to stand out. There's two differences that stand out between conventional plants and renewables that we believe change the way we should think about competition in these markets. Certainly conventional plants, they have nominal capacity. We know how much they're able to produce, and essentially most of the times they're available except for rare outages. But probably there's some type of incomplete information regarding the marginal cost of these plants, because these marginal costs, they depend on the efficiency rate of the plants, as well as on how much they pay, or what are the opportunity costs of burning their fuels, and there might be some heterogeneity there, as well as some private information. As we move from a fossil fuel dominated electricity system to one that is dominated by renewables, we are shifting to one market in which more or less we can think of marginal cost being quite homogeneous across these plants and being close to zero, but yet there's some uncertainty as to what the available capacities of these plants are. So we believe that renewables is going to be a game changer in how firms are going to be competing in this market, because this switch from cost being private information to capacities being private information is going to change the nature of strategic interaction among electricity producers, and this is what we want to understand. For those of you who are not familiar with this, just to convince you that private information on available capacities is a relevant issue, I just plotted here the forecast errors against production of the Spanish wind producers across several years. These forecast errors are published by the Spanish system operator, and you can see there are true forecast errors. They're centered around zero, but these forecast errors can be substantial. And things even get worse when it comes to solar production. We have even larger forecast errors. So we believe this provides us grounds to introduce the fact that available capacities are difficult to forecast as one of the main ingredients in our model that is going to be affecting competition in this market. So the main objective that we want to accomplish with this paper is analyze the nature and effects of a strategic interaction among renewable energy producers in wholesale markets. As I said, I think that this is relevant in its own sake. We want to understand how these markets will perform, but it's also key right now to understand investment incentives and to understand whether under the current market mechanisms these markets will provide the right incentives for those investments to already start taking place right now, or whether we need additional instruments like the ones David was discussing. Beyond electricity markets, I know this is an electricity conference, but beyond electricity markets, we believe that this type of problem might also be relevant to understand other auction settings in which we can also think of these maximum demand, for instance, in treasury auctions, how much treasury bills are banks willing to buy, as something which might also be considered to be incomplete information, and yet something that we believe has not been taken into account into the economics literature. So we know quite a lot. In this room there's quite a lot of people who have contributed to understanding competition in electricity markets. Most of the literature so far has focused on understanding competition in fossil fuels dominated electricity markets. Me and co-authors, we have made a contribution on trying to understand how electricity auctions work. Whenever firms know what the available capacities of the rivals are, and they also know the cost of the rivals for producing electricity. PAR here has recently contributed with a very interesting paper on how do firms compete in an electricity auction whenever there's incomplete information about their cost. And yet in this paper we want to move into this direction of trying to understand how do electricity auctions work whenever there is incomplete information, there's private information regarding capacities, but yet all firms know that their marginal costs are fairly constant and fairly low. Whenever we look into competition in electricity markets and we want to understand what happens in markets in which firms compete by using supply functions, either continuous supply functions or discrete supply functions, this is essentially the papers that we could spot as being related to ours. If we think of Cournot competition as a sort of supply function competition in which essentially firms are submitting supply functions that are vertical at a given capacity level, so it's essentially the steepest supply function that one can think of, there's also recent and interesting papers by people from MIT that also capture the fact that renewable available capacity can be uncertain, and what they find is that essentially in markets in which, for instance, there's both renewables and fossil fuel producers owned by the same firms, the price depressing effect of renewables can be mitigated by the fact that if firms can withhold output from their fossil fuel generators, they're going to do so, therefore mitigating the price depressing effect of renewables. Essentially, we also incorporate this uncertainty brought in by renewables, but we do so within a paper in which firms can compete both by choosing prices as well by choosing quantities, and we show that firms' strategies matter. This is going to affect the equilibrium. We are going to be able to see whether market power is exercised both by raising prices above marginal cost and or by withholding output. Essentially, we are going to give them the full range of instruments, either price choices or quantity choices that firms truly have in practice. If time allows, and Ben allows me to go through the whole model, my plan is to describe the model, describe as a benchmark what we already know about equilibrium bidding when capacities are known, and then provide the characterization of bid functions when capacities are providing information, and then compare the two to try to understand whether this intermittency of renewables is affecting market power and in which direction. We have a list of extensions. I'll do my best to try to cover at least the main messages out of those extensions, but probably there's not going to be enough time today to go through all these. So let me go through the model. It's really the simplest model we could think of in order to introduce capacity as a private information component to the model. We have two firms which are ex-ante symmetric. Their marginal costs are equal to C. There is no heterogeneity regarding or no uncertainty regarding marginal cost. You can think of these two firms as being renewable producers, with C being the O&M cost. Their capacities, their available capacities, are proper information. The capacity of firm A is distributed according to some CDF with some density in some interval which is known. Capacities, as of now in the baseline model, they're ID across firms, and they are private information of the owner. They're unknown to the competitor. Demand is assumed to be inelastic, and it's known. This can be extended to considering also some degree of demand uncertainties denoted by theta. And we assume that in this market there's some gas generators, this yellow area that David has in his slides. Not only there's a lot of wind, but also we also need to have some backup capacity in times there's not enough wind in the market. And for simplicity, we assume that this backup capacity is offered at marginal cost, and we assume that the marginal cost of these CCGTs is capital C greater than C. Essentially, you can think of this as an implicit price cap in the market that is put on the renewable producers because they cannot raise prices above that level, otherwise the gas producers will come in. What is the timing of the game? Essentially, every day before the market opens, each firm knows how much it's going to be producing. This is not really relevant whether the firm precisely knows how much it's going to be producing. What is clear is that whenever I submit my bid, I know how much output I'm putting in the market, and this is going to be affecting the market prices. So we can think of the firm as knowing how much output it has. Knowing that, it's going to be submitting to the market an inverted L supply function. Essentially, we are thinking of supply functions such that they have a single step, so the firm has to choose at which price, which is the minimum price at which they want to make available some quantity, and they can declare whatever they want as long as that quantity doesn't exceed their realized capacity. So essentially, we are allowing them to withhold output if that is what they think is optimal for profit maximizing. The pricing of the game essentially mimics the way electricity auctions work. The market operator or the auctioneer is going to call firms to produce an increasing price order. So the low price firm is either going to be covering total demand or whatever it declared it has available. The high price firm is going to be serving either nothing or the residual demand, and if the capacity declared by the renewable producer is not enough to cover total demand, essentially the residual demand is going to be covered by the gas producers. This is a uniform price auction, meaning that the market price is set equal to the highest accepted bid in this auction. And what we are going to do within this game, we are going to characterize the symmetric period strategy Bayesian-Nash equilibrium. Just a very simple figure, probably you are all very familiar with. If you can, this is just an illustration of how prices are set in this market. If we have these two firms that are submitting these supply functions, and if demand is above the declared capacity of the lowest bidding firm, essentially the market price in this market is going to be set equal to B2, and this is the price that both firms are going to be producing. As a benchmark, let's start thinking about something that we already know from the previous literature, which is what are the equilibria in this market if capacities were common knowledge, okay? And here in this diagram, what you have is the equilibrium bids and the resulting market prices as a function of the realized capacities of the two firms, and this is total demand in the market. When realized capacities together are not enough to cover total demand, essentially there is no competition among them, so prices are going to be set by the gas producers. Whenever both firms have individually enough capacity to cover total demand, there's going to be very strong competition, which is going to drive prices down to marginal cost. So essentially this is the Bertrand region with no market power. What happens in between, in these regions, at least one of the two firms is pivotal, meaning their capacity is needed to cover total demand. So here we find this asymmetric equilibrium by which one firm is bidding sufficiently low so that undercutting by the high bidding firm is unprofitable, and the other firm is simply left with the option of trying to maximize profits over the residual demand, and the best way it can do it is by raising the market price up to the marginal cost of the gas producers. So in this market, in all these regions, we have a market price equal to the highest admissible price in this market, which is the marginal cost of the gas producers, and a smaller region in which we have marginal cost pricing. We used to refer to this as the tale of two states because the market jumps from either being perfectly competitive to being almost perfectly collusive, okay? So in these two regions, these two firms are sharing profits very symmetrically because the low bidder essentially is making more profits, is selling all its capacity at the highest admissible price. However, whenever these capacities are common knowledge, they can correlate who is bidding high or low, for instance, by agreeing that the largest firm is going to be bidding high, and that's a proper way to symmetrically share profits in this market. So when capacities are known, the fact that bids can be conditioned on publicly known capacities allow them to get these seemingly collusive equilibria most of the time. What happens when we introduce intermittency? That is, what happens when we are not dealing with a market as we used to know it, in which capacities were common knowledge, to one in which capacities become private information? This is essentially what we want to do in this paper. So now I'm going to go through essentially what our contribution is. So we can think of each firm knowing its own capacity but not knowing the rivals. I can only condition my bid on my own capacity. I cannot condition it on the rivals, and I have to choose the prices and the quantities that I want to make available in the market. Essentially, the equilibria that we just found are only going to be valid in very special cases. For instance, in the case in which, regardless of the capacity realization, there's always going to be Bertrand pricing, in which case, even if we introduce intermittent capacities, we have marginal cost pricing. It's also going to be the same in the other very extreme case in which even if we have the highest realization of capacity, there's not going to be enough renewable capacity in the whole market to cover total demand. Again, the price is going to be set by the gas producers, but the relevant cases, the cases in which we'll probably see each other in 10, 15 years time in renewables dominated system is one in which, depending on the realization of capacity, we can fall in different regions. I'm going to be discussing mainly what we refer to as the baseline model. The baseline model is one in which firms are always pivotal. That is, even if I have the highest possible capacity, I never have enough capacity to cover total demand, but both firms on the aggregate, even at the lowest capacity realization, they have enough capacity to together cover total demand. And you will later see that if I allow for the other cases, essentially the characterization of the bit function equilibrium remains the same. Okay? So keeping this in mind, this is what the equilibrium looks like, and I'm going to try to help you understand what this is telling us. Okay? So first we want to understand what is the optimal bit that, given my realized capacity, I want to submit in this market. And essentially what this function is telling me is that firms, they add a markup on top of their marginal cost, and this markup is going to be a function of its realized capacity, which is captured by this function. Okay, this function is decreasing in my own realized capacity, meaning the higher my realized capacity, the lower is the markup at which I'm going to be submitting my capacity in this auction. Why is this so? Well, let's look at this function. What is this capturing? In the numerator, what we have is the quantity effect. That is, when I decide whether I want to marginally reduce my bid, what is going to happen is that if I reduce my bid and it happens to be below the bid of the rival, which is the case whenever the rival firm has a realized capacity equal to my own, if I reduce my bid, I'm going to be producing at capacity that is producing at K, rather than only producing the residual demand. Therefore, I'm going to enjoy a jump in my output, which is captured by what we have in the numerator. However, if I reduce my bid marginally, and I happen to be the high bidder because I have the low capacity, in that case I'm going to be reducing the market price, and therefore I'm going to be losing some revenues out of what I'm producing, and whenever I'm setting the price, I am selling only the residual demand. So what we have in this function, which is what is affecting my markup, is nothing but the standard trade-off faced by firms, a quantity effect and a price effect. And it happens that the quantity effect is stronger for bigger firms because the jump in output that they can enjoy when they undercut the rival is bigger because they have more capacity, and therefore larger firms or firms that have a higher realized renewable capacity, they have incentives to bid more competitively and therefore submit lower prices. This is the first result regarding which is the price at which I want to submit my output in the market. The second result is that in this baseline model, capacity withholding is never optimal. And the reason is, I believe, quite intuitive. If I happen to be the low bidder, I'm producing at capacity, so essentially I want to produce as much as I can, therefore I want to sell at capacity. If I happen to be the high bidder, I am serving the residual demand, meaning if I withhold or I do not withhold, essentially there's not going to be an impact on the market price. And if I withhold so much that the price jumps to the marginal cost of the gas producer, the profits I'm going to get out of it are below my equilibrium profits. So essentially what this proposition is telling us, yes, firms do exercise market power, but they exercise market power by raising price above marginal cost, not by withholding output. So if you want to have a figure of what these bidding functions they look like, so essentially this is telling us, as a function of my realized capacity, what is the markup that I want to add on top of my marginal cost, which here are assumed to be equal to 0.2. And as you can see, the optimal bid moves from the cost of the gas producers, which is assumed to be at 0.5, all the way down to my own marginal cost. And the reason is that, for instance, when I have the highest capacity realization, I know for sure that the rival is bidding above me. So for me, the best way to produce as much as I can is really by bidding at marginal cost, knowing that the rival firm is going to be setting a price above that level. So what are the implications? Of all this? Well, essentially, we know that renewables, they have a price suppression effect. Typically, when people have tried to measure the price depression effect, sometimes referred to as the merit or the effect of renewables, they assume that they are bidding to the market at marginal cost. If they add these markups into the bids, what is going to be the price depression effect of renewables? Somehow it's going to be mitigated, and our model allows to show the extent by which the price depression effect is mitigated or not. Essentially, what we see is that when realized capacities are larger, the whole supply function shifts down and out, right? Because when I have small realized capacities, I bid higher than when I have higher realized capacities. So when there's more available renewable capacity, the whole supply function in the market shifts down and out, leading to a much stronger price reduction, which is not as strong as if we had marginal cost pricing, but certainly there is a price depression effect which is stronger the more available capacity there is in the market. So if I want to understand the effect of renewables on market prices, then what I do is I compare the equilibrium outcomes that I just characterized with the ones we would have if capacity was common knowledge. And what we find is that essentially this intermittency destroys the seemingly collusive equilibria, so that renewables contribute to reducing market prices, not only because they have low marginal cost, but also because they help mitigate market power in this market, even though they themselves, they behave maximizing profits and therefore exercising market power. If I extend my model to cases in which there's at times whenever there is not enough renewable capacity in the market, I will be simply having the same bid function that I had before, but with a longer, flatter region at the beginning. So essentially the model extends. And another region which we believe is quite interesting and quite relevant when we analyze it is the case whenever there is so much installed renewable capacity that with some probability realized capacity of a single firm is enough to cover total demand. In this case, what we find is that indeed capacity withholding can become optimal. Essentially, a firm that has a realized capacity above total demand would rather behave and mimic the type as if it had capacity slightly below total demand. Why is this the case? Because by bidding very low at marginal cost for an output almost equal to total demand, the firm manages to sell almost total demand and yet have the rival firm setting the market price somewhere above. So indeed we find that sometimes capacity withholding is the right tool for exercising market power, but only in those cases in which there's so much installed capacity that essentially there would be excess renewable energy into the market. As we increase investing in installed renewable capacity, the probability that this is the case grows. So we'll have a lot of mass put at very low prices, and the whole market price will smoothly go down towards zero as we increase renewables into this market. With the minutes that I have available, let me tell you a little bit about the extensions we are working on. One is try to model strategic behavior among renewable producers when instead of having a uniform price auction in place, we have a pay-as-bid auction in place or a discriminatory auction that instead of paying winning bids the market price, it pays winning bids as they bid. So essentially we find an equilibrium that looks very much like the one I just described before. As a function of my realized capacity, I add a certain markup. Sorry, this should be a capital C rather than a capital P. We've been switching with notation, forgive me. So this markup is very similar to the one we had in the uniform price auction, but we have an additional term there. Essentially what this is telling me is that whenever I reduce the market price, I am affecting the market price whenever I am the high bidder, that is whenever I have the small capacity, but I'm also affecting my revenues otherwise, because now I get my bids whenever I produce, and whenever I'm bidding below the rival, and therefore I'm selling at capacity, even though in the uniform price auction my bid would be payoff irrelevant. Now in the pay-as-bid auction, it is payoff relevant because it's affecting my revenues. So essentially what we find here is that firms have weaker incentives to bid competitively, because now reducing the bid also translates into a low payment. So if I plot to compare them visually, the two bidding functions in the uniform price auction, the one we saw before, and in the discriminatory auction, what we find, similar to the paper by Parm, is that essentially when it comes to auction design, we are facing a trade-off. On the one hand, firms in the discriminatory auction, they are less competitive, right? But on the other hand, in the uniform price auction, I am always paying bidders the highest accepted bid rather than the low bid. So the issue is which of these two different effects dominates, and still the paper is not finished. All we've been able to do is to prove that there's no revenue equivalence between these two auction formats, and all our numerical solutions, they tell us, what we find here is that for the beta distribution, using the beta distribution for capacities, the two different parameters, alpha and beta, for all possible constellations of these two parameters that determine the CDF, always, even in the worst cases, the discriminatory auction results in higher payments to firms. So at least in this case, if we were to choose between a uniform price auction and a discriminatory auction, we'd rather go for a uniform price auction, because the competitive effect of these auctions is leading to lower payments to firms. We also look at the issue of oligopoly, and I'll be quick here. We extend the model to allowing for more than two firms, and we'd like to understand, so what happens when we have more than two firms? We have to do some fixes to compute the cumulative distribution function and density of the lowest capacity in the market, because that is going to be affecting how much I produce and what are the prices that are going to be set, okay? And essentially for firms that are pivotal, the decision of a single firm simply depends on whether it has the highest bid or not, and all the rest essentially remains as in the main paper, the main body of the paper. We can characterize the equilibrium in the same fashion, so now the markup is going to be affected by how many firms there are in the market, but the shape is similar. It goes down from the price cap in the market to its own marginal cost, and it shifts according to the number of firms. And we find that there's a pro-competitive effect of increasing the number of firms for the standard reasons as in other markets. But we thought that rather than increasing the number of firms, which would also bring in new capacity in the market, and therefore it's not surprising that if there's more capacity and there's more firms, there's more competition, we thought it would rather be more interesting to think about, if we have a given number of plants, how do we want to structure ownership? How do we want to split the ownership of the existing plants? And we performed the following example. Suppose that we have 4 plants in the market. Do we want to have 4 firms owning each of them one of these plants, or we rather have 2 firms, each of them owning 2 plants? And what we find is that there's an effect through competition, the standard pro-competitive effect. So the more firms we have, the more competitive the outcome is going to be. But we have an additional information effect, because if we split ownership among a larger number of firms, what happens is that each firm knows less about the realized capacity of the others. And this information effect somehow countervails the pro-competitive effect of increasing the number of firms, and therefore mitigates that pro-competitive effect. Yet, the pro-competitive effect of increasing the number of firms and fragmenting the market structure typically dominates. So what we find here is this is the bid function whenever there is 2 firms, and this is the bid function whenever there is 2 of them. And at least when capacity is not very large, the pro-competitive effect of fragmenting the market structure dominates. So let me conclude here. I hope I'm just on time. we believe that renewable energy is going to change the way we should think about competition in these markets. It really matters whether the source of private information is on cost or whether it's on capacity, and we believe we have provided the first, if not one of the first models that considers optimal pricing whenever renewable producers are strategic, and we allow them to play around both with prices as well as with quantities. We think this is just the first step, at least the first step in our research agenda. What we are really concerned about is whether those investments will take place and whether the regulatory instruments in place are indeed the right ones. And we just wanted to provide a solution to the second stage of the investment game in order to be able in future work to really look at the investment problem. Thank you so much.
Thank you, Natalia. Look forward to hearing about the solution to the first stage problem next time. So Hannes Fate will offer a question, and then we'll open it up for discussion among everybody.
So, actually I'm called the nemesis, but naturally I have to start with, the paper draft reads really nicely, so there isn't that much to criticize. It kept me nicely occupied while I was waiting 5 hours on the queue in Paris North because the French guys decided to go on strike on Sunday. So if you need something to read, I can forward you the draft. Being a nemesis, I have to criticize something. So I need to criticize now more from a practical side here. So there's nothing. It reads nicely. You can follow it, even if you're a numerical model or not so familiar with all this auction theory. I follow all the argumentation and I'm in line with you. Now, where I'm not in line is when I think about this second stage. Is that reality? Will that become out there, the bidding structure we see? Let me shortly jump back into this slide. Exactly. So that's the basic logic. So there's the I go in with manipulating my bidding prices. That's the whole reasoning. And I can follow why I'm not going with capacity withholding. But I think there's a pretty simple argument for capacity withholding, at least in Europe, which is called REMIT. REMIT is basically, we are monitoring all the market transactions we have in Europe. And that means all the biddings, all the information of the companies. And REMIT is there to figure out whether there's something not going nicely in the market. So basically anti-competitive behavior and structures like that. What they're looking for is, well, if you change your behavior suddenly, if there's a specific event and you bid differently, or patterns. Patterns. And I know if there's a company dominated by renewables, that pattern should look something like this, pretty flat. And if I take some time and see, okay, the pattern looks like that with their bidding, I'm pretty sure they're going to knock on the door of the company and make some nice discussion about competition law. So, because the information is obvious, if you are renewable, wind and solar, it's got to be zero marginal cost or close by. So whenever you go above in your bidding structure, at least in Europe with the monitoring we have, that's not a solid long-term strategy. I am not sure what's going on in the US. I'm also not sure whether REMIT will still be valid in the long run when we have a lot of renewables, because maybe we need different bidding structures there for the investment incentives. But for the current system, this would be a no-go. You wouldn't manage to get that through. And therefore, there's maybe an argument saying, yeah, I know why capacity withholding is not the optimal strategy, but maybe it's the one I get through with. Because capacity renewables, now that's something I can play around with pretty easily, even in legal sweat. Yeah, I wasn't sure what was the amount of capacity I have to bid because it's uncertain. So maybe that's for follow-up steps, figuring out, okay, how much do I lose if I need to go with capacity withholding? And the other one was, there was that slide where you said that you cannot bid it on the rival's capacity. That's the other argument where I think about what kind of market story are you telling me? I'm telling me a story where I have dominant large firms, oligopoly, duopoly. So in reality terms, it means really large companies. And if one thing is for sure of large companies, they are quite good with their trading departments, with their modeling departments, to know quite a lot about their rivals. And when you talk about renewables, you talk about sun and wind, so you know how the conditions are going to be. And even if you don't have the exact information about your rivals' capacity, you're still going to have quite some good estimation what their potential output may be. At least in the paper, you have some assumptions regarding the general forecast and things like that. I think that would be a way going forward in a sense of also from an investment perspective. Not being completely obvious, saying, okay, I have zero clue what the other guy is doing and I just need to take my own capacity. I know what the weather is going to be. I know what his capacities roughly are constructed of. So I have a rough idea what his capacity would be. And that's interesting from an investment perspective because likely depending on what mix of wind and solar they have, my investment strategy may be altered in a sense if I know my competitor looks like that. I have a competitive advantage if I go into that type of investment because then I'm kind of countering his pattern with a different injection pattern. But as I said, this is just going forward. The one is more like, be careful if you sell it to policymakers in Europe. And this one is, I think, really interesting when it comes to linking it to investment stage. But no real criticism to the structure you have so far. Okay,
Great.
that were my comments.
Thank you so much. I'm so sorry that you had to spend 5 hours in Paris, but I'm so glad you spent 5 hours reading my paper. So I'll benefit.
Like 4 or 3 because at one point you.
So I'll benefit from your comments later on. Let me just reply to these 2 questions.
Yeah.
First, regarding the issue of whether it's true that exercising market power through capacity withholding is less easy to detect from a regulator or from a market supervisor. I fully agree with that. But it's kind of dangerous because if the market operator is not going to allow in anything above marginal cost, so that they're going to be exercising market power only through capacity withholding, we end up in the Cournot model that is giving us more market power than this market design. So to the point that we rely on markets to set prices, it's very important to understand what are the effects of different policies regarding supervision, because we might be pushing firms towards even more market power than in this case. Okay. The second comment regarding how much do I know about my rivals? Well, the truth is the Spanish system operator does a great job at forecasting demands, and they do a best job in forecasting renewable output. This is the best information one can ever have because the system operator essentially constructs these forecasts by aggregating all the individual forecasts of the different plants. So this is really an information aggregator. So it has all the information available in the market with the best weather forecasts out there, and yet you can see that the forecast errors are substantial. Okay. So we believe that even if I know something about the rival, there's still some uncertainty that introduces this incomplete information. Of course, if all these forecast errors disappeared because all of a sudden we could do a great job at reducing them, then we would end up in the models that we already know, in which capacity is common knowledge, and we end up in the equilibria that we characterize and that we see in practice.
We totally agree on that. I'm not saying that there's no uncertainty left anymore. I'm just saying if you look even at that one, a large fraction is within a small range, so at least a large fraction of that capacity is still kind of known.
Yeah, this is what our GCDF function is capturing. That function is not really capturing the availability of renewable resources, but rather your forecast error. So your expected capacity is the average of that CDF, and what I'm modeling is really the forecast error. And as long as there's a forecast error there, as long as there's some private information regarding capacities, we believe this is affecting strategic interaction, and we believe this might be an appropriate way to think about it from a modeling perspective. Thank you so much.
Okay, thank you very much for. Unfortunately, since it is 5 a.m. California time, we do have to move on to the next speaker. I hope we'll have more.